Hi, Valeria.
Okay, hi, Alif. Welcome.
Thank you.
So, thank you very much for coming here today. We also organize a pool for you. So, just let me know when you want to start the pool, and I will, send the pool for the audience. During
Or maybe it's the easiest if we directly get it over and done with, and then I can follow it on the screen as well. So as a quick intro, I will be talking on some image diagnostics on the images that the camera on the machine is making. And just to get an idea of who is in the audience, I would like to ask a first question. Like how many of you, if you have metal printers, have a camera on that?
I sent the pool.
So, and there is a tab in the polls section.
Yes. So now we have just few answers, but they are coming.
Okay, I'm curious.
We are yes, no, and I don't have a metal machine. So we are more or less at the same level at the moment.
Okay, so a quick question then for the ones who do have the camera on the metal machine is, do you use then, do you use that camera or do you use these images?
So I sent a second poll. More yes, so people have a camera and they do something with the images. And in the chat, we have a person that say we use layer QAM and analyze images.
Okay, good to hear. So there is some familiarity with the topic then, I can say. Okay, then was there anything you wanted to say further, Valeria, or do I just start?
I let you exactly the
Okay.
stage. Please share your screen if you have a presentation and
Yes.
enjoy. Thank you very much, Liv. Thank you.
Okay, here we are. Here we go. So welcome all. Okay, the title became a bit long. It's when you start providing it in a Word document, you think you have all the space unless you have to start printing it on a slide. So as an image says a lot more than 1,000 words. This is what I want to be talking you about. It's all the things that can happen on a printer, and when you are confronted with this kind of situation. And this is actually a situation that was provided to us from my colleagues from the manufacturer's side. Because for the ones who are not familiar with Materialize, so we are a Leuven-based company, and I myself, I'm from the software department, so we develop software for everybody in the industry working with 3D printers. But as said, we have a manufacturing production side, so they make from prototypes till series production, and often we get their problems if they want to improve things. So it's for us very convenient that we have not one but also two production sites in it. We also have colleagues who are busy with medical production, like custom implants and other tools. But of course, there is a lot of synergy. Once we done things, we feed that back to them as well to help them in becoming better in what they do. because we are already for 3 decades. Materialise is more than 30 years old. In these early years, our focus was on making it work. Still think DOS and floppy disks. But then over the when years passed by, we focused a lot on meaningful applications, because we really think when you have meaningful applications, that's a huge driver for this fantastic technology and industry that we're in. But then also, and this is especially what I like as a software developer, we love this technology a lot at Materialise, but therefore, in order to compete with traditional technologies and so on, it's also important that we make it worthwhile. Can we make it economical viable? So what are things we could automate, diagnose, make sure there are less issues, that we can keep up a certain quality and so on? I think all these aspects need to be considered so that we can all together further boost this industry. So if I come back to this picture, it's not a ski slope. It's really Armageddon Day at the machine. And then as an engineer, you start wondering like, okay, first it's a bit like, oh my God, what happened here? But that's indeed then the question, what happened? What was the root cause for it? And can we remediate for that? And in order to find it out, and this is a picture from a P700 machine, we've put cameras on it so that we can take pictures from the machine. And you could see here what happened, and I'm going to go a bit back. So we had a culprit that made that already couple of solidified layers were dragged out of the powder bed, and then it starts acting as a broom over the powder bed, giving us Armageddon Day on the machine. So this one here, we called it the droplets of death. We're not shy of funky names. This really messed up that full build, and it's not one time that we notice it, but several times. And of course, if you have a full build, that's a lot of a crashed build, that's a lot of money that you have to throw away. So we were like on a quest. Can we find more out of these droplets that we see coming? And if yes, where are they? What could be the root cause and so on? But first thing first is, how can I find all these droplets or more about it? And you could think about manual annotations like a true Sherlock Holmes, but that's really like layer intensive. I mean, also know that in one build it easily goes over 10,000 images or more. It's very reviewer dependent. Also, it's very tough to keep focus on every image for so many times, and if you would have to do that day after day, also it will not be really repeatable, and there might be many glitches and missed things. So if you would look like, can we do it with more classical image processing algorithms, then that would be a bit semi-automatic, but the issue that you will encounter there is that typically lighting conditions, they play an important role. I mean, it can be already day or night, it can be shades being thrown differently from the recorder, whether it's left or right on your machine. It's just somebody switching a light on in the room. That will all have effect on the gray value scale of one image. And as such, you will end up with a lot of variation in your complete slide stack. So yes, there is some degree of automation, but with all these variances in gray values, for me to put it down as a quality inspection tool, I don't feel that's secure about it. So the next up is artificial intelligence. a solution? And I would say definitely yes, or at least that's what we expired. So if we bring it back now to metal, we need to know first, like, what will be investigating, what are issues that we can detect in the powder bed. And there are several. It's like a gap, so it's really the powder bed cracking open. We have like spatter and debris, often from the gas inflow. It's like spitting in the powder bed in a way, and then you get all these particles. There can be issues from the recoater. There is like a little dirt that got attached to the recoater, or some drag and wear in it that might start making horizontal stripes, like a scratch in the powder surface. It's also the short feet of powder that can give issues when parts start being elevated from the powder bed, when there is some warping. That's something that can be detected, and typically when you have some part elevation, as here is the beginning, that will often lead to vertical stripes. It's then that recoater that bumps on that part that started elevating, or on some other things. We have spotted sinkholes and craters, and also there can be like an overflow. So there are several things that can be spotted in a build, and that could have an effect on your part quality or on your build success. So just as a quick example, if we have to manually annotate it, I see here a glimpse of a stripe, and I could start annotating. I see here a glimpse of a stripe. I find here, I see a crater here, and it looks like there is something there. If we see what the software gets out of it, so okay, there is another crater there, and then the AI algorithm spots a stripe here that is there, but that for me, with my human eyes and with glasses on, was not really visible. So it's just showing this. It's like not always that easy. It's easy to overlook something, and some things just also sometimes with the light shading, when it's in the darker areas, it might be difficult to spot as a human. So when can you be happy? When you have an AI algorithm, because there is a lot of buzz around it. And as I said, we really want to put it in the market as a quality inspection tool. So for me, that validation is very important. And we have been doing testing and validation over a period of more than 2 years. We cooperated there with several partners, so external users, typically in quality critical domains like aerospace and medical device companies. In this, you already know, like when you can please two of the most demanding industries, then you're pretty sure you're okay for all the other industries as well. So when doing so, we also tested it images from a variety of machine, both brands and types, also with materials, because that also gives like often a different type of color. So of course, AI, it starts with self-learning. So we have manually annotated over 200,000 images to really feed to that learning pool. So that's pretty expensive and boring and cumbersome and tiresome, but a must to get good results. And we can say that by now, in all these testing and validation process, we have analyzed millions of images. So I feel pretty assured that we have a robust and reliable algorithm that is also machine, brand, type, and material agnostic. And we have a very high confidence percentage achieved on everything what we detect. So let's get out of the theory and let's look at some examples. So here, and let's get rid of that pen. So here you see like all the slices, and it goes very quickly, of production build of our medical production with many parts. And you will see there were quite a lot of scratches here. For the example we take, of course, the worst. It's not like that every day. So here you see a bit more highlight what happened here, but we got some warp of the part that also resolved like in a crater, and that we have been annotating. So the next step that we take then, because it's nice to have all these annotation in the images, it allows us to go more down. But what we do and what we've seen is extremely helpful. We start overlaying the issues that we find in the powder bed. We start overlaying that with a 3D model, and that really gives us an indication of where there could be damage to the part. And then, of course, in this case, the damage is so big you don't need a microscope or any additional tools to find that. I mean, that's obvious, but it's a nice showcase. And so we don't only have the visualization, but we will also translate all that information in data that can be used for statistics. So it all comes out and you get more data as metadata that you can use for other analysis as well. But as said, it's not always so obvious because, okay, this you immediately see it when you get from the machine, but it's not always the case. Sometimes it's a bit more hidden, and there are some more examples here. Like on the first one, we noticed that the support got detached as well, and you can see there were several things happening, so it indicates a spot. But I like very much this example, because if you see here on this area, something happened in the powder bed. On the part, it's not, and here it's a bit more zoomed in even, it's not directly visible. It's something that when you do a visual inspection, you might easily overlook. The part consists of a lot of lattice structure. So is this part of the lattice or is this something else? So by having these highlights and this kind of visual reporting already, this is like a caution to the people who do the inspection afterwards, like be careful, there are possible issues with this part. So it's like an alert and an attention drawer to a certain region. So this is another example where we had some, I don't recall if it was a vertical or a horizontal stripe, and this might be overlooked already more easily, but by having it again with that overlay on it, we know this situation here, and then I leave it to the specialists in the fields to make the decision. Is this part still acceptable, or do we need to scrap it? But at least you got the information, your attention is drawn to it, and then it's up to the experts to draw the proper conclusion on that. So knowing that we have, how could this technology influence on the process, or in the end, we always like to save on money and reduce costs. So how could this technology help in that? So as a quick refreshment, and you all know this, I assume, but it's like, okay, you do your build preparation, we have the print, and then typically you have still several steps ahead of it, like heat treatment, the post-machining, the surface engineering to have a nice polish, but also your verification and testing. which can be different types of testing, going up to full non-destructive testing in aerospace, whatever. So if we look at this three-flange hip implant, I mean, it's looking so great. It's so shiny. I can see myself in the reflection. For the ones of you with eagle eyes, is it really that great? Not really. So in that cavity here, if we zoom in, there is a lot of bad surface quality, and this part we had to throw in the bin. And this is really all these steps after the printing that has been all money down the drain, because we lost here a hip cycle, we lost a day on all these post-processing, quality inspections, all the paperwork, but then especially since here, of course, for series production, it is different, but in a mass customization where you have all one-offs, this is really when you have gone through all the steps, that's a week of lead time that you've lost. So if we would have known earlier, we could have started to rebuild already earlier and gained a lot of time also on that lead and delivery time to the customer, because in the end, you also want to keep your end customers happy. So if we would have the technology at that time, and we still had the images, we went back for it afterwards. So if we would have diagnosed it at that time, we would have seen we had issues. The 3D overlay would have given us that insight, and that area of overlap with issues is so big that we could have made the decision earlier in the process. So now our process is adjusted with an intermediate step where we do the automatic image diagnostics. And then depending on the outcome, we can say like, no, we are going to scrap that part immediately now. All the additional efforts that I would do is money down the drain, and we don't want to waste money and all the effort of people and so on as well. If it looks good, we can say go ahead. In some case, if there might still be some doubt, also there the team can make decisions like, okay, we expect some things, examine that area, it's maybe not critical, or we could it could still fall in between our quality criteria, or we could decide, not sure if it would come through. Maybe we decide to already launch a rebuild so that we don't lose time on the delivery there. So it will give you input. Of course, the team still needs to decide what is the next step, but at least you have some data where you can make decisions on, and it will allow you to save money or not, or make the right decisions. So if I start recapping, so how do we use at Materialize the software now in-house? So as I said, we have this feels a bit like me sitting with my colleagues of manufacturing and medical on a bench looking at all the gray value images. So how do we use it today? So we have the cameras on. We take the we do the image quality inspection, and one of the things that I did not drill down on, but that I start my story with, is we can use the information also as input for our process development, for our people who do machine maintenance and so on, and really use it as a root cause investigation. And to give you there a bit some feedback, remember this droplet of that from the beginning. So I already mentioned we can also gather all the metadata, and we can start correlating that with other measurements that we have taken on the machine. And I can tell you, when we just started with it, we have these, there is a saying that already goes a long, long time in the office. Sometimes it's like, yeah, when the weather changes, we have more build crashes. And then you think like, okay, has humidity, does humidity play a role in clotting and etc. So there can be a lot of things to look for. And the fun part, since we have these measurements on droplets on the occurrence, it's like when you changed a parameter and you start changing things, you can see was there an effect or not. It doesn't always immediately give you the real root cause, but at least you're not doing your tests blindly. You do have a kind of data feedback on it that can help you in doing root cause analysis and finding the culprit. So after many tests, we had also done tests where we had a sensor, a vibration sensor put on the recorder. And if we looked, so we have several P700s, all equipped with camera. We all measured vibration on it, and we could really see a correlation of the vibration on the recorder and the amount of droplets that were generated on average per layer for that specific machine. So as said, we have a lot of metadata available. Also, you can start counting in the axis correlator the vibration, because we also measured that in different directions. And we really could see also there in terms of peaks, when there was like more vibrations, we also had more droplets there. So we know where we need to make corrections on the machine, that we could avoid the amount of droplets, because they don't always are a droplet of that. They are not always causing that full mayhem and Armageddon day on the machine. So keeping that amount of droplets low definitely has a huge impact on build failures of the machine and build crashes, which again saves a lot of money. So this is a different approach on what you can do with that data, and then more with that metadata when you start pulling it up in Power BI, correlating with other data that you might have. It can give you a lot of insight there in your machine as well. So if we go back to our medical examples, and also if we see, I mentioned earlier, like in aerospace, if NDT is involved, then these post-processing and quality inspection steps, they can go up to like 70% of the cost of a part. So if we can say make an early decision, yeah, that is a lot of money we saved upon by not spending it. Yeah. So I think that's very crucial and very impactful, but it could also be on the quality inspection, like the in-between cases where you say like, okay, here might be something, we think it might still be good enough, but this is can be a high risk area. So make sure that is double checked and so on, so that you can assure your level of quality that you need in your organizations. So to conclude, there are, as we saw in the poll, people with the images, but the images by itself, it's not directly actionable data. It's not in an actionable format. It's not information. So by using an automated image diagnostics app, preferably based on AI, as we saw it, you start getting that actionable information. You start getting information where you can take actions upon, where you can see on the quality of the part. And the nice thing is, often these cameras are already in there, so it's not that you need to make additional investments in hardware. You just need a good software on it. And we've seen that by doing that intermediate quality check directly after the printing, you can avoid, in certain cases, by doing an early discarding of bad quality parts, you can really avoid that you send money down the drain and have useless costs there. It also will help you in that highlighting, but also what we've seen a lot, and that's often underestimated, it really facilitates teamwork a lot. As I said, often there is the data, it's in the cloud, there are the reports, so it can be shared between peers who do the same task, or if it's like the quality engineer, the data preppers, also the process engineers. So having all this data available for everybody, having it in a format that makes it pretty unique of what it's saying, so that there is no room for interpretation or misinterpretation or different interpretations, really facilitates that teamwork, so that everything gets better and more fluent. So if you have an interest in this, I would say contact us at this email address, and we will be happy to help you further.
Okay, thank you very much, Lieve. Very nice and interesting presentation. Unfortunately, we are on arrived at our time. We had just few questions. If you just can reply in very short time, how do you link a process defect on a defect on the component? Not every process instability leads finally to a part defect. Is there some kind of probability analysis?
Yeah, that's a very good question, if I understand it correctly. And it's indeed like, when is a defect in the powder bed, does that also lead to a defect in the part? And not everything. And there, with our medical department, we've seen, so for us, we've put somewhere a threshold, like if we have stripes in 3 consecutive layers on the same position, we know we will have bad quality. One stripe, that's not necessarily an issue, but multiple stripes can be an issue. And I think that is something that also reality, the in-house experience, will need to bring as well, and that will be then the next learning curve that we need to go through. Also, quality requirements are often different for different users. So we've seen
I
it.
think we lost you.
You hear me? I still hear you. And the last question, so it's really machine
Lieve, I
again.
lost you.
Mm.
I cannot hear you.
I think we can still hear you, Lieve, if you want
Yeah.
to finish
Okay.
answering that
So
question.
on that last question, as I said, so it's not dependent on one brand or type. It's really a very robust, super duper algorithm. So we've tested it on multiple ones, and I'm confident that we can easily transfer it to other machines. If there would be still some things differently, we can further train the algorithm, but in its current states, I mean, it worked on everything we've put in there. So yes, it can be transferred, and it's pretty agnostic, so that it's great.
Great. Thank you so much, Lieve. I will take over now while we work through these technical issues. But thank you so much for your presentation. And now we will move on to the next portion